Hello, everyone, and welcome to the ECOM seminars. So we are really pleased to have today Matthew Coggon from CIRES at CU-Boulder down the road. Matthew came in 2015 as a CIRES visiting postdoctoral researcher, and then he transitioned to research scientist one at CIRES. So it's very nice to have Matthew here, and we are looking forward to it.
Awesome, thanks, Juan. Thanks for having me. It's really nice to be able to come down the road and share what we're doing over at NOAA. Today I'm going to be talking about work that we've been doing to try to understand a new and emerging source, I shouldn't say new, but emerging source of pollution. And I always like to frame it with our favorite test subject, Los Angeles. And what I generally study is urban air pollution, and traditionally we think of urban air pollution in places like Los Angeles to be dominated by vehicles, but over the past 50 years, as I'll show you, we've seen a dramatic reduction in vehicle emissions, and now new things are coming out of the woodworks, such as consumer products, and that's what we're focusing on now. I'm going to present work on behalf of Brian McDonald, who couldn't be here, his new science paper focusing on these emissions, specifically in Los Angeles. And I'll also talk about work that we've been doing in Boulder and also in New York City. So this work isn't done in a vacuum. Of course, I'm going to present Brian's work, and many of the co-authors on this list collaborated with Brian on his science paper. And we've been fortunate enough to also work with a lot of people outside of NOAA. So Environment and Climate Change Canada worked with a study that we did in Boulder. And we had a lot of help with the New York study that I'll talk about from the City College of New York. Fred Moshari and Mark Arend were very instrumental in making that happen. So like I mentioned, talking about urban air pollution. So I want to start with a picture of air pollution as we traditionally think about it. So thinking back to the 1940s, when LA, you couldn't see your neighbor's house, pollution was largely dominated by vehicle exhaust. And as Carson Wernicke showed in a 2012 paper, that the emissions associated with vehicles for many different VOCs have dropped dramatically over 50, 60 years at a rate of about 7.5% per year. And that's concurrent with an increase in fuel usage. So despite increasing fuel usage, threefold increase, the improvement in catalytic converters and fuel efficiency have allowed us to reduce vehicle emissions substantially. And that's had huge implications on secondary air pollutants like ozone, and as well as secondary organic aerosol. Whereas in the 1960s, you would have walked outside and you would have been breathing in 400 ppb of ozone. Today, 100 or less. And that isn't just in Los Angeles. We've seen that across the country in major urban areas. So data from NASA's ozone monitoring instrument has shown huge reductions in NOx across the country. Again, concurrent with our improvement in vehicle emissions. And vehicles have gotten so clean that there are actually very few that are contributing to the total pollution associated with vehicle exhaust. This is data from Gary Bishop over at DU. If you've ever driven along I-25 onto Route 6, you may have had your vehicle exhaust sampled by Gary. So Gary has an instrument, an OpenPath IR instrument that can measure vehicle exhaust in real time at the tailpipe. And he's done this over decades. And what he's found is that newer vehicles just don't emit that much. So if you look at the model year, anything younger than 2005 does not emit that many VOCs or that much NOx relative to those produced in the 90s and 80s. And it's gotten such that the dirtiest 10% of the fleet contribute 80% to hydrocarbon NOx emissions. So in general, that's a great success story. But despite those successes, we still have a difficult time attributing aerosol concentrations specifically in places like Los Angeles. So here I'm showing work by Patrick Hayes in 2015 paper where they tried to model secondary organic aerosol during the CalNEX study. And what they found is that if you only included vehicle emissions, you could account for a very small fraction of the SOA that's produced over the course of a day. And there's this huge, 75 to 80% gap where the amount of SOA you would need, or the amount of precursors you would need, largely resides in a semi-volatile or intermediate volatility pool. And so what Patrick concluded is that there must be something other than vehicle emissions contributing to the missing secondary organic aerosol that's formed in a place like Los Angeles. And so that leads to this question, are there other sources aside from vehicle emissions that can explain this missing source and that could be important? And so this motivation is the big driving force behind what Brian McDonald did in his recent science paper. So the title, Volatile Chemical Products Emerging as the Largest Petrochemical Source of Urban Organic Emissions. This is the source of potential missing SOA precursors that we want to look at. And his paper made a lot of spicy headlines. If you want cleaner air, try using less deodorant. And that's the heart of this. If you want to improve your air quality, we need to start thinking about these components of the petrochemical industry. And so I'm going to go through how Brian did this work and its implications for urban air quality. And our starting point is a mass balance of the petrochemical industry itself on a national basis. So if you were to start with on a production basis, what you would find is that the majority of what we produce from extraction of oil and natural gas goes into combustion. So about 502 teragrams goes into natural gas, 381 goes into gasoline, and only a really small fraction of that goes into the feedstocks that we use to make consumer products, about 6%. Of that 6%, a fraction of it is to produce ethylene and propylene. Ethylene is used to generate plastic and rubbers, and propylene goes into the organic solvents that go into your deodorants, hair gels, etc. If we go down the chain a little bit further, of those organic solvents, we can break it down into different categories: pesticides, coatings, cleaning products, and personal care products. Now, all of this comes from a litany of data, sales, which you can get from government censuses and from census statistics, not census statistics, but Bureau of Money. So you can get that from these government agencies, and you can estimate this based off of the taxing information, right? So we keep track of that, and you can estimate sales based off of those numbers. Now, you look at this and you think, okay, this is a really small fraction of the total petrochemical industry. How does this translate into emissions? How can such a small fraction of that actually contribute significantly? Well, it does so because what we generate for energy purposes, we combust. So the majority of what we put into our vehicles actually gets converted into CO and CO2, which doesn't have implications for urban air pollution. So back in the 1960s, before we put in catalysts, we would have had very large VOC emission factors from your vehicle. But today, we've decreased those by several orders of magnitude. Contrary to that, we do not combust what we put onto our bodies. It's purposely designed to evaporate. So if you put on your personal care products, whatever you put onto your body, a large fraction of that will be emitted. And so the emission factors of these personal care products are significant, orders of magnitude more than what comes out of your vehicle. And that translates to emissions that are comparable to what you would see coming from vehicle exhaust or from natural gas production. Okay, so these upstream emissions, these are from the direct emissions from oil and natural gas production. These are from mobile sources. And then these are our VCPs. And so Brian wanted to understand this, and he built this inventory, and now I'm going to show you how he tested this using data from the CalNEX study. So CalNEX was in 2010. We had extensive VOC measurements on platform at Caltech. The data I'm going to show you largely come from the GC instrument, which Jessica Gilman operated. It's important to know that the meteorology is pretty well understood in this area. So during the day, you have flow from the ocean towards Pasadena. And so that picks up a lot of the emissions from Los Angeles and then is detected at the ground site. In the evening, it's pretty stagnant and you're mostly sampling local emissions. So here is the footprint that we're considering around the tower at Pasadena. And so the way Brian modeled this, he took that inventory that he developed, and then he treated that footprint like a box where you have air moving in, you have fossil fuel emissions from vehicles, which we can estimate fairly well. He's done a lot of work to understand these vehicle emissions. And then this is the real key. We take those emissions and we have a model for the exchange of indoor emissions from within a building to the outdoor environment. So most of the emissions occur while we're inside. We spend most of our time, about 80%, indoors. And then there's an air exchange rate of about an hour, and that's typical for most buildings. So you have emissions, it's exchanged with the outdoor air, and then it's picked up in the model. And so what I'm going to show you is a comparison of the measurements at the CalNEX site to Brian's emissions inventory. So if we look at it as just a scatter plot, a one-to-one scatter plot of what the observations were versus the box model, and box model at age 0 just means the emissions that were put into the model itself, you find that we do a pretty good job with a lot of compounds that are typical of fossil fuels. So xylenes, toluene, for example, naphthalene. We get very good agreement when we only look at fossil fuel usage. What we're missing, however, are oxygenates and heavier alkanes. And one specifically is ethanol. So we dope our fuel with a lot of ethanol, about 10%. So if you were to think that ethanol, you would initially think that if VOC emissions were strictly due to vehicles, that ethanol would be very well predicted, but it's not. Neither is isopropanol or acetone, and we have significant biases on average, about 39%, and the R-squared is not all that great. But when we include this indoor to outdoor exchange, so we have these indoor VCPs included in the model, we start to see very good agreement. The bias goes away. We can predict ethanol very well. And the same with acetone and isopropanol. So we go from absolutely no chance of predicting isopropanol to now landing on the one-to-one line. Of course, we're missing a few VOCs. So these open circles are carbonyl compounds that could potentially be coming from other processes like cooking or even chemistry that we can't account for in the model very well. So there's still work to do, but for a lot of the compounds that we believe to have no real big secondary sources like ethanol, we start to predict it very, very well. So with that, we have some confidence in the emissions inventory. And so what does this mean for air pollution? So if we break down that inventory, this is what it looks like in a total VOC space. So upwards of half of the VOCs come from these consumer products. So about 15% are treated as industrial VCPs. These could be used in the production of say, PDMS, for example, polydimethicone. And then 38% comes from these consumer products, your deodorants, your hairsprays, paints, solvents, etc. And then a much smaller fraction actually comes from gasoline and diesel exhaust. So what does this mean in terms of VOC reactivity, ozone potential, secondary organic aerosol potential? Well, it's half. So if you look at the published rate constants and you apply these and estimate a OH reactivity, you find that, again, about 50% of it can be attributed to consumer products. And the same holds true for secondary organic aerosol, though the error bars on this are much larger since we have to estimate this using Chris Kappa's SAW model. And so using some assumptions, you can get an estimate of the secondary organic aerosol yield, apply that to your VOC data, and you find that, again, we expect about half of it could be from these consumer products. And so it leads to the question, are these what is responsible for the secondary organic aerosol that we see in a place like Los Angeles? Is this missing chunk of the pie associated with these VCPs? And we have a lot of work to do to get there, but this gives us the basis for field work that I'll start talking about next. Now, another motivation, you might look at Brian's work and think, great, we've got it, we can maybe stop. Not really, there's a lot of work we need to do, specifically in understanding the composition of these emissions. So if you look at fuel emissions, there's not a huge difference between natural gas source, evaporative gas vapors, gasoline exhaust, diesel exhaust, the same types of compounds, alkanes, aromatics, alkenes, those are going to come out of those sources. But when you look at something like a consumer product, you see huge differences in the composition across different sectors. So a degreaser is going to be not very rich in oxygenates, whereas a hair care product or a perfume will have a lot of it. Right? These are the things that are water soluble, that allow them to be used on your body. So the composition is drastically different from between different categories. So that means that these all have different impacts on SOA and ozone formation. Another reason that we want to study this is further from a field standpoint is that we've done a lot to understand what the fuel emissions are, what's in them. And so most of the composition data that we have actually comes from field measurements, whereas consumer products come from CARB surveys of industry. So the California Air Resources Board sends out a survey asking what's in your products, and they send that back to CARB. So when you look at these surveys, certain components, certain major components will be listed under a general heading, such as fragrances, right? So what is a fragrance? That can be hundreds of compounds that have different reactivity, different SOA potential, right? So there's some muddy waters in here, and it means that we have to go out and actually make these measurements. Furthermore, we don't know what the emission factors for all of these are. We know what's in it, but how much actually gets evaporated and makes it into the atmosphere? That's the second question, and why we need to do more work on this. So we need better constraints on VCP emissions. We need to understand how these are exchanged with the outdoors and what these impacts could have on SOA and ozone formation. And specifically, if we could start to understand what tracers are unique to each industry, that would be really helpful to constrain the emissions from a top-down standpoint. So if we can start making measurements of VCPs, maybe we can find specific compounds that are unique to each category. And so I'm going to talk a little bit about work that we've done in this realm, specifically on personal care products. So if you were to go to your bathroom today and go through all your personal care products, I would bet $5 that every single one of you would find this compound in something, right? It's called cyclopentasiloxane. It can also be called dimethicone. It can also be called D5-siloxane. It is a cyclical silicon oxygen ringed molecule that has a very surprisingly high vapor pressure. And it's used in these products to give a silky smooth feeling. So if you ever put on a gel deodorant, it's one of the major components that allows it to spread nicely either on your hair or wherever you apply deodorant. And it's primarily produced for deodorant and hair care products. About 70% of its production goes to deodorant, and about 20% goes into these hair care products. Some amount also goes into the production of polydimethylsiloxane, so that's that black silicon tubing that we use in our laboratories. A small fraction goes into the production of that, but that's mostly driven by D4, which is the 4-silicon analog to this compound. And there's actually a lot of it out there. Alan Goldstein's group has studied this in indoor environments. They've made measurements of engineering classrooms, and as students go in and out, they monitor the VOCs that are emitted, and the cyclic volatile methylsiloxane, CVMS, make up about half of the VOCs. Then of that pie, D5 is the major component, right? So this seems like a really good tracer for consumer products, for personal care products. And they're actually really interesting because much like Brian's work, these also get spicy headlines where they're very pervasive in the environment. So people have measured them in Chicago air. They've measured it in Atlantic cod livers. So it gets into the ocean, and then it has some bioaccumulative properties. It's found in human breast milk. It's found on the International Space Station. It's everywhere. So there's a lot of reasons that we want to measure this compound for various understanding its presence in the atmosphere more widely. And I like this picture because it kind of points out how much of this stuff we actually use. When you use your personal care products and you put it into a landfill, if the landfill uses the gas that's produced as a combustion source, they have to actually put in equipment to strip out siloxanes. Because if they don't, when it's combusted, it generates silicate deposits that can ruin your turbines and then coke up your heat exchangers. So there's so much of it that we use that it's also a big issue for industry to remove after they put it into our products. So we went out to try and measure this compound. And we did this by just throwing a tube outside our lab and sampling for a month and just see how much of this stuff is out there. So we sampled at the top of our roof. If you've ever been to NOAA, this is on the northeast corner of the building. Winds generally come from the north. This was during the winter of 2015 from December all the way through January. Generally the winds came from this direction and picked up emissions through Boulder. We also did mobile sampling, so we took our mobile laboratory and sampled throughout Boulder in areas impacted by residential areas, industrial areas, as well as open space to try and get a gradient in these emissions. The data I'm going to show you come from our proton transfer reaction time of flight mass spec. The details of the instrument, if you're not familiar, are not hugely important, and I'd be happy to discuss them afterwards. But generally what we can do is we can measure hundreds of VOCs at 1 Hertz resolution. And we have very good sensitivity to D5-siloxane. It has a very unique fingerprint in our instrument. It has very strong isotopic pattern. And so when we see this mass, we know definitively that it's D5-siloxane. So let me jump into the measurements. So what I'm showing you here is the time series of D5-siloxane in blue over just a few days. And over that, I'm also showing concentrations of benzene. And in general, in Boulder, we see about 10 ppt all the way up to 100 ppt during really stagnant days of D5-siloxane. But what's most striking about this is not necessarily the absolute values, is the covariation with benzene. So when we see a large spike in D5-siloxane, it's concurrent with these spikes in benzene. And you look at the diurnal patterns of this, and you see that in traffic periods. So in the morning rush hour, you have a spike in siloxane that is concurrent with a spike in benzene. You also see that in the evening, albeit D5 is a little bit lower. And the correlations between these two are very good. So the morning rush hour, we get a correlation about 0.75 between D5 and benzene. And we get a correlation slightly worse in the afternoon, but still in a slope that's about half that of the morning. So you look at this and you think, what's going on here? You're telling me this is from personal care products. Is this actually coming from vehicles? Well, we have a lot of evidence just looking at this to say no. One, the ratio of D5 to benzene changes throughout the day. It's actually decreasing. And we see that if we look at it on an hourly basis. So we actually have a morning D5 to benzene peak that decreases throughout the day. This is in green from our ground site data. And these 2 points come from our mobile measurements when we're in residential areas. So in general, when we're measuring at our site, we see a trend that's consistent throughout Boulder where D5 to benzene ratio is highest in the morning and decreases. So that would suggest that it's not coming from vehicle exhaust because you would have a constant ratio to benzene. And so what we hypothesize is that maybe it's actually coming from the people inside the vehicle. So maybe as people are driving around, their emissions are mixing with their tailpipe emissions. So to test that, we did some cute experiments where we all participated by sitting in a car, and I would just measure the cabin air and see, do we see the highest concentrations of D5-siloxane inside the car that's then emitted once we either open the windows or turn on a cabin fan turn on the cabin fan. And that's exactly what you see. So when someone enters the car who has applied products that contain D5, we see concentrations upwards of 20 ppb inside the cabin. When we turn on the cabin fan, which is here in orange, we see a sharp decrease in these emissions or these concentrations. And we measure enhancements at the back of the vehicle where these emissions are intended to be released. And it's repeatable across different people who've worn D5 that day. Of course, there are a few people who haven't perhaps put on their deodorant that day. And I refrained from saying who that was, but we don't see those enhancements for people who didn't apply D5. So what we conclude is that it must be coming from the people inside the vehicles, the commuters. So that's one way that these correlations can exist. Another is that we think that there's actually overlapping emission patterns as well, not just that they're co-emitted from a source that is co-located, but that these emissions have overlapping patterns. So to show that, we drive through Boulder in our van, and we go through different areas that are impacted by residential emissions. This is in blue, that's a little hard to see. Commercial areas that are in gray, CU-Boulder, and then we have some open space measurements even at the top of NCAR here. And what you find is that D5 emissions are enhanced in residential areas, as you would expect. So this could be that people put on their personal care products in the morning, and these, like Brian's model showed, can be exchanged with outdoor air, and so you see these enhancements. They happen to also be concurrent with enhancements in benzene as well, although we do see benzene higher along roads and in commercial areas as well. But what this suggests is that you have this area source of D5 that is likely mixing with an area source of benzene. And we attribute that to you put on your deodorant in the morning and you leave your house and you start driving around, right? So they may not be coming from the same place, but those emissions are eventually going to mix, and that's what we're going to sample at NOAA. And that's kind of summarized here. So this diurnal pattern is a combination of two things. One, it's associated with the variability in people driving to and from work. That's one reason we see an afternoon peak in D5, is we believe that people are traveling close to the inlet at NOAA, and we see these enhancements in both D5 and benzene. But then in the morning, we have both a big spike in D5 because of the same reason, but likely this larger, more gradual increase and decrease in D5 throughout the day is likely due to the overlap in emission patterns that are concurrent with benzene emissions. So what I'm going to do now is we're going to do a cute little trick where we take that D5 to benzene ratio and try to estimate a emission pattern. So if I've shown that the correlation between these two tracers is relatively strong, if we multiply the D5 to benzene ratio by an estimate of benzene emissions that we can get from an inventory, then we can start to say something about the emission pattern, the diurnal emission pattern of this stuff. And so that's what I'm going to show here. In gray are benzene emissions. This is Brian's work. He has an inventory of the Denver area based off of traffic counts and known emission factors from vehicles, so we can get a handle on what the benzene emission rate is. When we multiply that by the D5 to benzene D5 to benzene ratio, we get a emission pattern that seems to make sense. We get that morning peak when people apply their personal care products that then decreases exponentially with a time constant of about 9 hours. And that time constant is consistent with indoor measurements. So Alan Goldstein's group also sees about a time constant for these emissions of about 9 hours. What's striking is that the emissions of D5 are comparable to benzene in the morning. So benzene is about 2 to 2.5% of vehicle exhaust in terms of total VOC mass. The same is true for D5 siloxane. And so what that means is that on a total basis, the amount of VOCs that are coming out of your car when you are driving from your personal care products is on par with the amount of VOCs coming out of your vehicle, right? So when you are driving, you are emitting just as much of these pollution-inducing VOCs as your vehicle. So from this data, we now have a way of tracing personal care products. This seems like a great marker for trying to understand these emissions. And we're in Boulder. So Boulder seems like maybe not the greatest place to understand these emissions. There's not that many people. People tend to maybe wear less personal care products than people in maybe a major city. It's just a hypothesis. So where do you go if you want to actually measure these things, if you want to understand this? And so we went to Manhattan, New York. So comparing Manhattan to New York, it has about the same land area, but the population is an order of magnitude larger. And the amount of driving that people do in Manhattan is actually significantly less than that in Boulder. So actually 70% of the population in Boulder, I didn't know this until I looked at census data, 70% of the population actually drives to work. I thought that would have been different for Boulder where people bike a lot. But in fact, most of us drive. And so we actually drive a lot, 24 miles per day to get to and from work. In Manhattan, it's impossible to drive. So most people take the subway. And so actually the average daily drive per person is about 9 miles per day, right? So on a relative basis, if you want to look through the weeds and see how much do VCPs matter, you have to go to some place where there's a ton of people and not that much driving happening. Now I say that there's still a lot of driving happening, but on a relative sense, we should see these signals much, much greater in Manhattan. We also have an additional motivation to go in Manhattan, and this stems from Brian's work. So Brian's work estimates that each one of us uses about 1.5 grams of fragrances per day. Now, what's in a fragrance? Fragrances contain largely monoterpenes. So limonene, alpha-pinene, beta-pinene. Those are what make us smell like pine trees and mask our odors, right? It's what we're just emphatic about this stuff. We put it into our trash bags. I mean, it's like everywhere. So from that estimate, right, you can scale up what the emissions of monoterpenes would be in a place like Manhattan. So in Brian's paper, he estimates about 30 moles of carbon per square kilometer per hour in Los Angeles. In Manhattan, that could be close to 260 moles of carbon per square kilometer per hour, which is much greater than what you would expect from, say, a dense forest. So our additional motivation is there a large non-biogenic source of terpenes in New York City, right? Is there a fragrance use that outcompetes with emissions from a dense forest? And we have evidence in Boulder to suggest that that might be the case. So here are the time series of monoterpenes that we can measure with our PTR versus, or laid on top of our trace for D5-siloxane. And you actually see fairly good agreement. So the variation in monoterpenes largely follows that of D5-siloxane. So it makes you wonder, is it a tree or is it some other tree? And you know, the diurnal of monoterpenes actually matches D5-siloxane fairly well. So we have, again, a morning peak here and then an afternoon peak in monoterpenes that seems to coincide fairly well with D5-siloxane. So that provides some evidence that this should also be, we should see this type of behavior in a place like New York City. So no more than a month ago, we went there. And we set up at the City College of New York, which is at the top of Manhattan in a very, very densely populated area. We set up on the roof of the engineering building right next to Alexander Hamilton's house. So if you've seen the play, that is where he lives. And we sat there for 5 weeks. 3 weeks, and just measured air in uptown New York. And then every once in a while, when we felt like we could handle it, we drove through the city. So we drove from the top of Manhattan down to the bottom. For reference, it takes about an hour and a half to go one way. So we did one day where we drove that loop 3 or 4 times. So that was a 12-hour day of driving through Manhattan. And then we would also drive out to these areas of low population to get some contrast. On the mobile laboratory, we had a PTR TOF. We had a whole air sampling system that we then analyzed here with Jessica's GC. And then we had CO, CO2, N2O, and methane. There was a lot of challenges in this campaign. It was called the New York Investigation of Consumer Emissions, or New York ICE. And when we were there, we happened upon the 4 nor'easters that hit New England. And it turns out that we were there during the cleanest time of the year. So these are CO measurements from the ambient monitoring station near CCNY. And for all of 2018, up till when we showed up, it was fairly dirty. And then we show up and the whole place cleans out. So what I'm going to show you, take with a grain of salt. They were at the lower end of what we could see. We did manage to measure this little pollution event at the end. And so you'll see that in the data. So let's look at the monoterpene and D5 traces, much like what we did with Boulder. What you first see is that there's a lot of stuff going on here. There are lots of spikes in D5 and monoterpenes. These are short spikes. These are not, hours long. These are from individual sources transiting by our inlet. But then there's this broad agreement in the diurnal pattern that's a little hard to see here. But again, we do see this morning peak in D5-siloxane that decreases throughout the day, and we see a double hump in monoterpenes. Towards the end of the campaign, when we finally had a stagnation event, we see enhancements in these concentrations up to a ppb for monoterpenes and around 300 ppb for D5-siloxane. So fairly significant concentrations, even though these were relatively clean environment. So this tells us that there's lots of variability in monoterpenes at our sampling site, but what does that mean spatially? Can we start to compare the measurements outside the city to investigate, is this truly anthropogenic, or could it be from the 20 trees that are in New York City? So first I'm going to show you D5-siloxane. So this is a distribution of D5 we drove from rural New Jersey through over the George Washington Bridge, and then sampled throughout Manhattan, and then out towards the Bronx and Queens. And what you see is really big enhancements in D5 in these highly densely populated areas like downtown Manhattan. And what you can do is you can take those maps of population density that I showed you earlier, and if you calculate along our drive path the population density at every point, and you average on a longitudinal basis, so you can see the gradient in population density and D5, you see that D5, which are shown as these bars, has really good correlation with population density, right? And this correlation has an R squared of about 0.7. So there's very good agreement. When we are in more populated areas, we see higher concentrations of D5 siloxane. And the same is true for Boulder. So if you do the same analysis, but now going on a latitude basis, you see that same correlation where the hotspots of D5 are in the Pearl Street area, right around the Pearl Street Mall, where we have a lot of people walking around, putting on perfumes, buying things, what have you. So what does that mean for the monoterpenes? Well, we actually see these urban enhancements as well. So when we're out in rural New Jersey, we see some enhancements of monoterpenes, and we think that this is likely due to residential wood burning. Here we're in the middle of a forest away from any town, and we see pretty much nothing. There were very, very, very low concentrations of monoterpenes. But as soon as we transit into the city, we start to see, again, this urban enhancement that has a fairly good correlation with population density, right? The tails outside the most populated areas, we do see some enhancements. But again, there seems to be this urban enhancement. The real kicker is our instrument can only measure the total monoterpene signal. How about the monoterpene speciation? Because that will tell us something about whether this is natural or not. And so this is fresh data. We don't have it in terms of ppb yet, but these are normalized counts of our monoterpene tracers, limonene, alpha-pinene, beta-pinene. Limonene is typically what they put into consumer products. And what you see in the last 24 hours where we had that big stagnation event, you see that we largely have limonene. It's the biggest component of the monoterpenes. And if you look at specific samples, so this is a sample that we took in the Lincoln Tunnel where there's no tree in sight. And you can see that the majority of the signal that we see is associated with limonene. And then when we go to rural New Jersey, limonene is largely reduced, and we mostly have alpha-pinene and beta-pinene, which is what you would expect for a forest like this. So again, the fingerprint suggests that there's this non-biogenic source of monoterpenes, that what we're measuring with our SIMS is not just, is most likely associated with enhancements in limonene and alpha-pinene, which are very common in fragrances. So where do we go from here? This monoterpene story isn't the only thing. We measured a lot of stuff. And so we're now trying to look at tracers. What other things could be out there that could tell us about these different VCP sectors? So D5 was great for personal care products. But we also see things like D4 siloxane, as I talked about before. And what's interesting is that D4 has almost no correlation to D5. And that's largely because D4 is not in D5. It's actually a regulated compound. They've found that it has some toxicity in the EU, and so it's been banned in European countries. And now we have restrictions that are likely to be implemented in the US. But we mostly find D5 siloxane in things like adhesives and coatings, so it has industrial applications. So it may be a good tracer for more industrial siloxanes. We see nitromethane. I didn't know this until I talked to Bill Dubé one day, and nitromethane is apparently a drag racing fuel. So there's no drag racing that I would know of in New York City. I don't know how you would do it, but it's also present in dry cleaning. And so on every corner in New York City, there is a laundromat. And so potentially this could be coming from dry cleaning processes. It's used as a stabilizer for the chlorinated compounds that are used to clean your clothes. And we see large variations, upwards of 200 to 400 ppt of this stuff. And then we also see chlorinated, fluorinated compounds. So this is para-chlorobenzene trifluoride. And it's been added to coatings, coating mixtures and cleaners as an alternative to toluene. If you look on the internet and you try to understand, how much or where this is coming from, it's not a restricted VOC, so the coatings industry does not call this a VOC, but our data suggests that it is. We see quite a bit of it, upwards of a half a ppb. And again, it has some correlation with D4-siloxane, so the fingerprint for coatings may contain both of these compounds. So I show this because this is prime data to do either principal component analysis or some sort of PMF analysis to start to look for fingerprints. And so moving forward, we're going to start with that analysis to see if we can pick out specific tracers that are unique to each of these industries, and perhaps maybe even pull out full VOC fingerprints. So I'll leave it at that. Conclusions that we have evidence from modeling and from our field work that consumer products are emerging as a major source of urban VOCs. We're finding tracers like D5, and we need to do more to try and constrain these other emission patterns. We found D5 as a great way of constraining personal care product emissions. Perhaps these chlorinated compounds would be good at looking at solvents. And then we need to also, in addition to the terpene emissions, we need to start understanding what impacts these have. And there's been very little work to understand specifically how do these form secondary organic aerosol. The only paper that I'm aware of is out of David Cocker's group at UCR. And they put a couple of compounds that are common in consumer products into a large chamber and did SOA experiments. And what they found is that there is secondary organic aerosol potential. Glycol ethers with this green trace here and this very, very light blue trace, which you can't see, generate 10 to have a SOA yield of 10 to 20%. So there is the potential for these to generate SOA, and so we need to start maybe putting them into chambers or into flow tubes to start to quantify that. And that's it. I'll take any questions.
Thanks, man. Thanks, Matt. Very interesting. Are there any questions?
So actually I have two. One is, what is the lifetime of D5? And the other was and you had it on one of your slides, so maybe I missed the explanation, but your mixing ratios of the D5-siloxane were about the same for Boulder and New York. Right. Is that right? Yeah. So what does that say about, obviously there's a lot more people in New York than there is in Boulder, so either we use a lot more or, so what's the explanation for that? Yeah,
I'll start with that one. So the explanation for that is that we were there during the cleanest period. So the winds on average were 10 to 15 miles per hour while we were there. So we never really actually got the stagnation that we saw in Boulder. So Boulder, in the evening, you would get the nocturnal boundary layer, and so you'd see concentrations that would be fairly high. Whereas in New York City, there's no such boundary layer formed because the winds were so strong. So we were in the cleanest period, and we did start to see major enhancements towards the end. We would expect, and just based off of the CO, let me just pull this out. Based off of the CO emissions that you would routinely see in New York City, we'd expect to see much higher concentrations. And you can see that here, where if we had measured in February, we would have likely seen much, much higher concentrations than in Boulder, a factor of 2 to 3 higher, we expect, than what we saw in New York City in itself. I forget your second question, or your first one. The lifetime of D5 is about a week, so it's a little bit longer than benzene.
More questions?
What are the sinks of D5?
Yeah, D5, the primary sink they believe in the atmosphere is via OH oxidation. There's evidence to suggest that it forms aerosol. So work out of Johnson Murray's group has shown silicon nanoparticles in Los Angeles. And that can't be formed from dust or any physical process. It has to be chemical. So one of the hypotheses is that these can undergo chemistry to nucleate and form silicon oxide nanoparticles. And then it can be lost via wet deposition, but the primary sink is believed to be OH oxidation.
So are you going to do a new measurement in New York because you were unlucky when you went there?
We were.
Number one. And number two, do you think, is that an American problem, or do you think in other cities of the world
That's a good question.
that situation would be similar or maybe different?
Yeah, that's first one. We probably will not be able to go back to New York in the near future, but that would be great. We actually think in the summertime you'd probably have higher emissions, potentially because you would have more evaporative emissions, but also people open up their houses and you have more exchange. And we also don't know how these things are lost to surfaces. So in your home, you could lose these to the walls, or you could lose some of these to the venting systems. So maybe in the summer you have higher exchange rates and it has a chance to actually make it outdoors. So there's a lot of questions there, summer versus winter. And then as whether it's a problem in maybe a European city or other places, we think that there's evidence to suggest that species like ethanol, you see a seasonality in ethanol in London, for example, where ethanol is twice as high in the summer as it is in the winter. Now, unless they're completely reformulating their fuel, it has to be coming from another source, and maybe it's these evaporative emissions. So on that basis, perhaps, but maybe people use less fragrances, maybe people use less D5. I know D5 is, for example, going to be phased out in wash-off products in the European Union. So it may not be a great tracer in Europe, but there's likely to be other compounds that'll matter, and that will be just as good as D5.
So what about making further investigation indoors? Because, what comes out is also uncertain a bit.
Yeah.
So you could get more information by just making measurements in houses of people who use these products or maybe don't use them so much?
Yeah. Well, that's work that's happening at CU right now. So Joost, Jose, Paul Zeman, they're actively doing that right now to look at indoor emissions. From our standpoint, we think we need to do both ends because what they're finding is that a lot of these, especially oxygenated compounds, are lost to the ventilation systems and to the walls, and they undergo chemistry too. Terpenes, if you have ozone in the room, you can react away a lot of your terpene emissions, for example. So I think you have to do both. You have to look in the outdoor realm and say, what do we see? So we see this chlorinated, compound that tells us that there must be some source of it that could be from these solvents. And we think kind of joining those two is a good approach. But you're right. I think that's ultimately where a lot of Brian's emission factors, they come from just industry reporting that. But to get down to the total emissions, we have to understand the whole system, the exchange, and then how much gets outside. And so doing both, I think, will help. Yeah.
I have a quick question. So what do you think it will be the best approach to include this new information into the models, like chemistry models?
Yeah. So one question is when do the emissions happen? And so from the D5 standpoint, we think that you could take this emission pattern and scale what you think your inventory is to an emission pattern that looks like this, where you have a peak in the morning and then a decrease throughout the day. And so if you're doing if all of your emissions are happening in the morning, then that has a chance to undergo chemistry. And so that's an important piece to implementing this into a model correctly. And so that kind of gives a handle on personal care products. For these other compounds, we need to understand the diurnal patterns, and we just don't. One way you could do it is to measure building exhaust, right? And like do that for a bunch of places and start monitoring different VOCs and understand their diurnal patterns. The other one is, we're going to try and take these tracers that we're seeing in New York and see if we can do the exact same thing here where we get out these diurnal patterns. The last piece, I think, is then to do PMF to get the fingerprint. So once you have the tracer, you apply whatever fingerprint you can constrain for personal care products, solvents, et cetera. And then you can maybe start to have a handle on the total VOC emissions.
Are there more questions? If no, let's thank Matt.